A scanning electron microscope is about the size of a large desk. The column is to the right, extending above the specimen chamber, on the front of which can be seen the external stage controls. All of these components rest on a vibration isolation table, built over a cabinet full of vacuum valves, plumbing, switches, and an oil diffusion pump. Behind and to the left of the column, above it, the cylindrical liquid nitrogen dewar for the X-ray analysis system can be seen. The back of the secondary electron detector, a rectangular box angling just above the specimen chamber, is to the left, and one of the backscattered electron detectors projects horizontally out of the specimen chamber to the right. Almost all of the controls for the microscope are available via the computer, accessible through the monitor and keyboard. Computer control is what makes this microscope remotely accessible. The microscope has its own filtered electrical power, with mains matching transformers and a high-tension tank that produces up to 30,000 volts, a closed water system or chiller to cool the electromagnetic lenses, dry nitrogen gas backfill, pressurized air to control the valves, and rotary vacuum pumps. It's networked and runs 24 hours a day. The sample is placed inside the sealed chamber of the electron microscope, which must be pumped to a relatively good vacuum before we can turn our primary electron beam on. Air molecules anywhere inside the electron microscope could be collided with, sending the electrons far off course. Collisions with air molecules are unacceptable when trying to maintain reliable image sharpness and minimize noise each time the microscope is used. This image is of the inside of the electron microscope. It is taken by a small CCD video camera and illuminated using infrared light. The camera is necessary to verify that movable components on the stage won't impact the column or chamber when the door is opened and closed. It is invaluable when attempting sophisticated orientations or using complex apparatus like the Peltier cold stage, where it may be important to see the sample as the vacuum pumps down. With this camera, we can see the pole piece out of which the primary electron beam comes. Directly below it is the sample stage, which has 5 axes of motion, although tilt is not yet computer controlled. When we use the scanning electron microscope to image a specimen, we are directing high-energy electrons, the electron beam, at the specimen in an ordered pattern, left to right, line by line, in a repeating rectangular array. The high-energy electrons, which may also be termed primary electrons, cause secondary electrons to be ejected from atoms at or near the surface of the specimen. Some of these secondary electrons, at least 1,000 times less energetic than the primary electrons, are collected using a secondary electron detector, or SED. The SED has a metal cage at its entryway with a 300-volt positive bias on it that attracts the secondary electrons. The cage, also called a Faraday cage, can bend the paths of secondary electrons in the direction of the SED so that they travel through the Faraday cage towards the collection target of the detector. The analog signal being produced by the SED in real time is sampled by an analog-to-digital converter and synchronized to the position of the primary beam along its raster path. The computer converts the digitized analog signal into pixels of varying gray level, one by one, left to right, line by line, in concert with the movement of the electron beam across the sample. Thus, we never take an instantaneous snapshot of our field of view as with a CCD, but rather must build the image pixel by pixel over the time it takes for the primary beam to raster over our entire field of view. Magnification is achieved by simply making the field of view, the rectangular area over which the beam travels, smaller. A scan area 1 micron wide will result in an image 10 times more magnified than a scan area 10 microns wide. Magnification is just one way in which the techniques of light microscopy and scanning electron microscopy are completely different. As a reference, atoms range in diameter from 1 to 3 angstroms, and there are 10 angstroms per nanometer. So in the space of 2 nanometers, there could be from 6 to 20 atoms. Even though our beam can be reduced to a diameter of only a few nanometers, we must take into account sample penetration when we discuss how small of features we expect to resolve. Sample penetration is not just important to resolution. It also causes unexpected phenomenon such as edge effect and many other less frequent phenomenon in all modes of imaging. Most of the secondary electron signal that we see in secondary electron mode comes from type 1 secondary electrons, which escape only near the surface where the primary beam strikes. Backscattered electrons, however, may bounce back from even further inside the sample. X-rays, typically created by backscattered electrons that never made it back out of the sample, are known to come from the deepest areas of beam interaction. Secondary electrons may be generated at all depths of beam interaction. However, their weak nature causes all but those occurring near the surface to be recaptured by the sample before they are able to escape. Secondary electrons come from the surface and very near the surface of the specimen, and thus the secondary electron image represents mostly topographical information. If the specimen is tilted towards the secondary electron detector, the signal will be much stronger and the image much brighter. This is something we often forget because the signal obtained using a field emission electron